Hello and welcome. This video is a set of solutions to select problems from the RL Practice Exam. This is Dr. Loza's practice midterm that's posted up on Carmen for midterm 3. So the first question for today, or for this video, is magnesium 2 plus is smaller than sodium plus. Both of these ions have 10 total electrons, so they're isoelectronic with each other. Magnesium is smaller due to its higher charge. The magnesium nucleus has a 12 plus charge. Sodium's only has an 11 plus charge. And so it doesn't have anything to do with electron counts. Magnesium and sodium have the same electron counts, so A does not make any sense. B, magnesium has a greater mass than sodium. This holds electrons more tightly. Magnesium does have a greater mass, but it's not for that reason that makes it have a greater charge. Magnesium 2 plus has a greater atomic number than sodium, thus it holds electrons more tightly. The greater atomic number gives magnesium more protons. Magnesium has a smaller ionization energy than sodium. That is actually not true. Magnesium would actually have a greater ionization energy, so D is just categorically not true. So the only explanation that's true and correctly explains the trend would be statement C. So the next question, consider the first ionization energy of 3 unidentified elements from the third period, that means the third row. Place them in order of decreasing ionic radius. Okay, so we're given ionization energy. One of them is 578, second is 521, Z is 1012. And so from left to right, ionization energy increases. So from left to right, it would go X would be next, then Y, then, or excuse me, Z would come next, and then followed by Y. So my ionization energy generally increasing from left to right. Now, of course, there are these periodic inconsistencies, but these are a small inconsistency. These are pretty big jumps in ionization energy. So I think that's how we can tell that Y is going to come last from left to right, then Z in the middle, and then X will come first. And so now to actually get the decreasing ionic radius, this is by order of ionization energy. Y should be the smallest, so Y is going to be smaller because it's further to the right and has a higher effective charge, hence the greater lattice energy. Then Z, X should be the biggest. So it should be X less than Z less than Y. Which pair of elements both have acidic oxides? So it just means if the element is an oxide you would classify as being acidic, that would be a non-metal oxide. So we want to choose 2 non-metal atoms. Tin's a metal, lithium's a metal, aluminum's a metal, calcium's a metal. Some of these are somewhat hard without maybe knowing for sure or double checking a periodic table, but only E would contain 2 atoms that are both nonmetals. So selenium's a nonmetal. If you go one down, tellurium would be a metalloid, but then phosphorus is also not a metalloid, it is a nonmetal. So both of these are nonmetals. Nonmetal oxides, when dissolved in water, leads to acidic solutions, so often nonmetal oxides are called acidic oxides. So this question here, arrange the following oxides in order of increasing acidity. I'm not entirely sure that this is entirely the most fair question to think of for our midterm. The idea here, though, I believe, is that if you have your basic oxides for your metal oxides, that we're going to be increasing in acidic character as we go from left to right. And so then we can also maybe come up with a couple analogies that that chloric acid is a strong acid, so a strong acid character is increasing as we go from left to right, and also perhaps upward, because again, that chlorine is a particularly strong acid. Okay, so my weakest acid, the increasing acidity, the least acidity should come from metal oxides. So B is looking to be the most, well, among the most correct trends, because I have 2 metal oxides. I have the calcium and the aluminum oxide. But the calcium is to the left, then aluminum, then silicon. Carbon is higher up on the chart. We actually know carbonic acid is an acid form. I've never seen any acids of silicon, so I might expect carbonic acid would be more acidic than silicon, then phosphorus, then sulfur. So B is looking to be, to me, to be the most correct. The least acidic, these don't make any choices here, or make any sense here, because these are relatively highly acidic metal compounds. They're going to make things like sulfuric and phosphoric acid, which are relatively high in the acidity side. And calcium oxide is certainly a basic oxide, not a very highly acidic oxide. So a strange question, but it's just getting us to think about how the basic oxides are on the left side of the periodic table, the acidic oxides are on the right, so we must be increasing towards acidic oxides and acidity from left to right. So then question 7 here, the alkali metals react with water. Which one's the most reactive? Well, if we think about the reactivity trends of the metals, we would probably expect the larger alkali metal to be more reactive, because the reactivity here is the reaction of something like sodium to react with water to lose its electron and give those to the hydrogens to make H2. So we're going to make H2 gas, and then hydroxide ion, and then sodium cations. And so then we're making sodium hydroxide. We need 2 of those. We're going to need 2 waters to give us our H2 and our 2 sodium hydroxides. And so we can balance the reaction. It's not a big deal per se. I don't know if you should necessarily know how to write that reaction. I think it makes sense because we're thinking of sodium. We know it's dissolved in water, so make the cation, and then leave behind hydroxide ion, and then making H2 gas along the way. And so the larger the further down we go from top to bottom, the lower the ionization energy, the easier the metal is to ionize. So something like cesium has the lowest ionization energy of the atoms in this group. So cesium would lose its electron most easily, hence it should be the most reactive. So continuing along, an element X reacts with oxygen to form XO2 and chlorine to form XCl4. XO2 is a white solid that melts at high temperatures above 1,000 degrees C. Under usual conditions, XCl4 is a colorless liquid with a boiling point of 58 degrees. What do you think about the identity of X? Okay, well, let's think about this just a little bit. So if X is a metal, then this should have been ionic salt. So this should have been an MCl4 ionic compound, which should have had a high melting point. Likewise, if X is a non-metal, then when it makes XO2, like think about CO2 or SO2, those are all gases at room temperature, then we wouldn't expect something like CO2 or SO2 to have a very high melting point, and the XO2 compound has a very high melting point. So it's not consistent with the X being a metal, because the XCl4 should have been an ionic compound, hence having a high melting point, but it doesn't have a high melting point. And if it's a non-metal oxide, and then we would have expected that compound to have a relatively low melting point, which it does, but then we would expect that, the non-metal oxide, the XO2, to have a low melting point, but it has a high melting point. So the only thing that we can say is that X would most likely be some sort of a metalloid. So maybe it's something like silicon. So silicon SiCl4 has a relatively low melting point because it's not a metal chloride, but then SiO2, we'll see this a bit more in chapter 12. This is actually glass, something like quartz, which has a very high melting point due to a sort of a big network of covalent bonds this type of molecule forms. And it forms those sort of as a consequence, perhaps, of the metalloid nature of silicon. And so the best thing I think we can describe here is that the element X is most likely a metalloid. Bit of a weird question, but we're just trying to see that one compound's more consistent with a non-metal trend, one's more consistent with a metal trend, hence that sounds like a metalloid, an element that's sharing properties of both a metal and a non-metal. Number 9, which statement is false? So we're looking for the false statement. Elements from the opposite side of the periodic table tend to form ionic compounds. That sounds true. So that's not one of our correct answers. Lattice energy is the energy given off when gaseous ions combine to form 1 mole of an ionic solid. That sounds false. Okay, so that sounds like the false statement because lattice energy is the energy of the ionic solid that it requires to be absorbed for it to form its gaseous ions. So this sounds like the inverse of what the true meaning of lattice energy is. Let's go through the other choices. Hopefully see that they're true. The type of compound that is most likely to contain a covalent bond is one that is composed only of nonmetals. And that is generally true, that our nonmetals tend to form covalent bonds, and metals and nonmetals together tend to form ionic bonds. The ability of an atom to attract electrons to itself is best quantified by electronegativity. Oddly, I think this is almost false, but I suppose it doesn't sound to be more false than statement B. Statement B I know definitely is false. The thing I don't like with this statement here, the ability of an atom to attract electrons, it should be in a bond to itself. Because otherwise, the ability of an atom to attract electrons to itself sounds like electron affinity. So the difference between electron affinity and electronegativity is that they aren't exactly the same. Because like F doesn't actually have the most negative electron affinity, but it does have the most positive or the most desire for electrons in bonds. So I think we have to separate the idea of the desire for electrons in bonds with other atoms versus just electrons by the atom itself without necessarily forming a bond. So fluorine doesn't as negatively accept an electron into its shell as chlorine does, it turns out, but then F does pull electrons more closely towards itself than chlorine. So if we're comparing HF and HCl and the partial negative charges that end up on the ordinary zero formal charged atoms, HF is going to have a bigger dipole, not as big of a dipole because chlorine's not as electronegative. So the partial negative charge on the chlorine not as big, the magnitude of that negative charge on fluorine will be much bigger. All the above are true. I think that's an annoying statement, but nope, B is incorrect. Okay, let's move on. So the substance ClO, important in the depletion of ozone. The ClO molecule has a dipole moment 1.24, a bond length 1.64 angstrom. The only thing I would say this problem here, you would have the conversion factors given. That's one of the reasons why I chose this problem. You would still have 1D is 3.34 times 10 to the minus 30 coulomb meters given. I think it was neglected from this problem. Maybe it was on an equation sheet somewhere else. And then one electron has a charge of 1.602 times 10 to the minus 19 coulombs. So you're using mu is equal to Q times R. Q is equal to mu divided by R. We're taking into account our units, so you can work out Q pretty easily. The thing I wanted to come back to on this question, this may have been a slightly tricky question had it asked for the actual charge in the atom and for us to figure out which one's more negative and which one's positive. Okay, so when we work out the arithmetic, I think it should work out to answer B. So I wanted to spend a few moments on is that most likely we're looking at a single bond between Cl and O, and this has oxygen with a zero formal charge, 6 minus 1, 2, 3, 4, 5, 6 electrons surrounding it, 7 minus 7 for chlorine, so it has a zero charge. Oxygen is more electronegative. Oxygen is the second most electronegative compared to fluorine. So oxygen goes negative, chlorine goes positive, so the charge on chlorine would be plus 0.162 units of an electron, and then the charge on the oxygen would be minus 0.162 units of an electron. Just kind of coming back to the issue that if this question's asking for which atom's minus, which one's plus in this compound, well, we just start with the Lewis structure, think of the formal charge, then kick in electronegativity, and think about the polarity of the bond pointing towards the oxygen, making it partially negatively charged. So moving on to 13, the electronegativity difference between A and X is 0.8. What statement is true about the compound AX? The bond probably doesn't have as good of a electronegativity difference for the substance to be ionic, but this difference isn't exactly, I don't even think it's in the book anymore, to be honest, that if your difference is about greater than 0.4, then generally we classify that as being polar. Less than that, generally nonpolar. If you're greater than a difference of about 2, usually we consider that substance to be ionic. But I also think it's true that there's a lot of compounds that we would consider ionic that don't have a difference greater than 2. And so we had mentioned earlier in the class, and I think there's this in the book too somewhere, that usually you would just compare the melting points. That if the melting point of a compound is relatively high, that's indicative of it having mostly ionic character. And if the melting point is relatively low, then that's indicative of the compound having non-metallic character. That's what I was using to characterize that problem above, that the XCl4 with a low melting point indicates it's most likely some non-metallic character for that element, not a metallic character. So the compound has a dipole moment. Okay, the electronegativity difference between A and X. It's true about the compound AX. Yeah, so if we have a diatomic molecule and the atoms differ in electronegativity, then the molecule should be polar and have a dipole moment. The bond in this compound is covalent. I would say it's covalent just if the difference, less than 2, or just, if we know something about the melting point being relatively low for the compound. So that sounds to be true. The bond in this compound is polar covalent. That sounds good too, because the difference of electronegativity is pretty big. A and X are different from each other. The compound is likely to be a brittle solid at room temperature. I mean, solid structures come up a bit more in chapter 12. So I'm not quite sure why we'd be talking about solid structure here. A brittle solid would be something more indicative of an ionic compound, like sodium chloride is a brittle solid, whereas I don't know if we necessarily think of something like ice or something like sugar as necessarily being as brittle. So I think when the answer goes with 2, 3, and 4, the bond in the compound is covalent. Maybe that means nonpolar covalent is what the question's meaning, because I think the answer went with 2 and 4. They must be taking that to mean nonpolar covalent. If you ask me, all due apologies to whoever wrote this question. I don't like it, so I wouldn't worry too much about that question. 15. Formic acid has 2 resonance structures. Which of the following are true? So H, C, double bond O, single bond O, lone pair, in resonance with this C, single bond O, lone pair, double bond O. And so we have 2 resonance structures. The real molecule should exist as the composite with delocalized bonding. The actual structure of formate switches back and forth between the 2 resonance forms. That is categorically incorrect. That is not how resonance works. Resonance works by taking the leftover p orbital that's here in this structure here, and this leftover p orbital, and likewise the p orbital in carbon, and it spreads those electrons out in that type of an orbital where those electrons get distributed across all these atoms simultaneously through one delocalized bond. That makes all the bonds equal in length. So each of the carbon-oxygen bonds is somewhere between a single and a double bond. That is true. Both bonds would be equal in length, indicative of a bond order of about 3/2. The actual structure of formate is an average of the 2 resonance forms. That is a better statement of what resonance, how to describe resonance, is it's more of a compositing of the 2 structures. And then each oxygen has a double bond half the time. Not true. It has a double bond none of the time. It always has a 3/2 bond at all times. So 2 and 3 are our true statements. 16, which of the following is true? For nonmetals, the addition of the group number for nonmetals, the addition of the group number and the number of single bonds equals 8. Group number. Okay, so the group number is on the periodic table. I've never thought of that before, I guess. So oxygen's in group 6, and it forms 2 bonds, so I guess that would equal 8. Carbon's in group 4, so it would form 4 bonds, I guess that equals 8. Okay, so that oddly sounds right. I can work that out pretty easily. So that's just looking at our group numbers from left to right, being alkalis 1, alkalines 2. I don't know if all of us Chem 1210 instructors really look at group numbers as being something that we all use as a term anymore, now that we give common exams. So chlorine oxides, in which the chlorine is bonded to one of more oxygen atoms. It's probably supposed to say 1 or more oxygen atoms. Which is bonded to one of more chlorine oxides, in which chlorine is bonded to 1 or more oxygen atoms, obey the octet rule. It's supposed to say or, I believe. Obey the octet rule. Like ClO2. So I don't know, like, so that's 7 plus 2 times 6. I don't see how they can all violate or obey the octet rule, because they should have an odd count. So that doesn't sound true due to the odd count. So something's going to have to break the octet rule. It's not going to be oxygen, because they get their octets by our Lewis structure rules, and then we'd have a total of 12 plus 7, that's 19 electrons. So we'd have 16 distributed, and so we'd have not quite an octet. Maybe we make a double bond. So either we're deficient or we're expanding an octet of chlorine, one or the other, for ClO2. So statement 2 doesn't look to be true. For the third row of the periodic table and beyond, the octet rule is often not obeyed. I mean, I suppose in the way that we write Lewis structures, but we've talked a bit in class about how real atoms only make molecules with really electronegative atoms to pull electron density off the atom. So I'm not sure what it really means when somebody says an atom violates the octet rule. Maybe in a Lewis structure it does. If you look at something like SF6, I think it's silly to think that this molecule or sulfur truly violates the octet rule without thinking about the actual charge on sulfur. So I suppose statement 3 sounds correct by the way people tend to use the vernacular of the octet rule, though it doesn't make a lot of sense to me to use it that way. So I think 1 and 3 should be right. I am peeking at the key and it is right. So 2 is not right, I guess, because of the odd count. I'm looking at the key where it's using a chlorine oxide ion as the example. I think chlorine oxide should be taken to be quite specifically an uncharged ion, or an uncharged molecule, and not the ion by the wording of the question. So you shouldn't be considering ClO3 minus. And if you do consider ClO3 minus, you can sketch a Lewis structure where it obeys the octet rule. So I don't know. Weird question here. I wouldn't focus too much on some of these questions that don't cover material or have a slight bit of a different vernacular than what we're currently using in a class like ours. 18, which of the following is false? The centers of charge in a polar molecule do not coincide. The centers of charge in polar molecules do not coincide. I don't even know what that means. I'm going to come back to that one. The molecule I3 minus exists, but F3 minus does not. Well, let's look at I3 minus. I've never thought of this before. Never even considered it. 7 times 3 plus 1. That's 22 electrons. So we'd have I. Lone pairs all the way around. And so that'd be 16 electrons. So we're going 1, 2, 3 pairs of electrons on I. So F3 minus would not exist because F would have to expand its octet in the Lewis structure, and we should never have, even in a Lewis structure, a second row atom violating the octet rule. Those types of compounds just don't exist. Like SF4, SF6 exists, things like PF5 exist. If you do these with like nitrogen, NF5 doesn't exist, OF4 doesn't exist, OF6 doesn't exist. So we have second row atoms and their Lewis structures obeying the octet rule, even in the Lewis structure. Third row and beyond, we can break the octet rule in the Lewis structure. So that would be a correct statement. There is a strong relationship between the formal charge, oxidation number, and oxidizing potential of the oxyanions. Well, okay, let's think of this for a minute. So ClO4 minus is an oxyanion. You know, I don't even necessarily know how to think of the formal charge because it depends on what Lewis structure you might write. One where you have the formal charge is minimized. A strong relationship between formal charge, oxidation number. The oxidation number here might make a link here. We've never quite, at least in lecture, talked about the oxidizing potential of oxyanions. That's not something that comes up in the textbook for a while, so I'm not quite sure how to approach that particular topic. Turns out I've just glanced at the key that C is the incorrect statement. I mean, I think C is incorrect just because we don't even necessarily have a good indicator of what the formal charge of chlorine would be, because there's multiple different Lewis structures we might think are just as good as each other, or potential Lewis structures that differ in formal charge. So I guess C perhaps is false for that reason. So usually you get a connection between the oxidation number being the same sign as the formal charge, but not necessarily the same magnitude. But anyways, moving on, bond length is related to the number of bonds between two atoms. Yes, so a double bond is shorter than a single bond, shorter than a triple bond. So D is definitely a correct statement. E, the molecule chlorine dioxide does not satisfy the octet rule for every atom in the molecule. I guess for the same reason we were using that, I just happened to use that in an example earlier, but an odd electron count would not be able to satisfy the octet rule by the standard Lewis structure rule, so that would be a correct statement. The centers, so going back to A, the centers of charge in a polar molecule do not coincide. I just don't even know what that's supposed to mean. I don't know. So I still don't know what that means, but C just doesn't make much sense to me, so we'll go with that as the right answer. 21, ZCl5 minus has a square pyramidal shape, square pyramid. Which of the following could be Z? Okay, so we need there to be one lone pair and 5 bonding pairs here, so we're going to need a total of 5 times 7 plus 1. That's chlorine's count, that's 36 electrons. I need to get up to 42 total electrons, so I can put 4 electron pairs around each of the chlorines for a total of 8 electrons for each chlorine, and then have 2 left over for the lone pair. And so I'm going to need 6 electrons on whatever Z is in terms of its valence count to get the 42. So I can have phosphorus. I can have something like sulfur, have the 5 chlorines, 8 electrons each, 2 electrons left over. So I want that to be something like sulfur. Which of the following is polar? SF6, that's octahedral, definitely nonpolar as a result. Xenon F2, linear molecule, that's nonpolar. Xenon O2, so that'll be 8 plus 6 times 2, so that's 20 electrons. And so Xenon O2 should look like a Xenon O, lone pair. So we have lone pairs around the oxygen. Even if you do double bonds or whatever, you still have the lone pairs and still in a tetrahedral type geometry. So that's looking like a strong indicator to be polar. So we have these bond dipoles pointing towards the oxygen. CH4, not really a polar bond, but even if it was, we have the tetrahedron geometry, so it's not going to be a polar molecule. So that would be perfectly nonpolar. I3 minus. We did that Lewis structure earlier. It was a linear molecule because it was like xenon F2 with the trigonal bipyramidal domain. So that was a linear molecule. And I was basing that off of what we already saw for that molecule a couple slides ago. Which of the following statements is correct? Triple bond consists of 2 sigma and 1 pi. That's incorrect. It's 1 sigma, 2 pi. Sigma results from head-to-head overlap of atomic orbitals. That sounds correct. So that just head-to-head just means head-on orbital like this. And so free rotation may occur about a double bond. Like a double bond is really locked in place because if we rotate the double bond, we're going to break the pi bond. So we can't rotate around a double bond. Pi bonds have electron density on the internuclear axis. Pi bonds have electron density on the internuclear plane, not on the internuclear axis. Sigma have their electron density on the internuclear axis. So sigma bonds would be true for that statement. More than one of those statements is true, that's not the right answer, so it would just be B. All right, so 25 statements are true. Electrons are never found in an antibonding orbital. That's not true. We can, like O2 has antibonding electrons and it's a perfectly stable molecule. All antibonding MOs are higher in energy than the atomic orbitals from which they are composed of. That is true. Antibonding MOs have electron density mainly outside the space of the two nuclei. That is true. So none of these are true. It doesn't make sense. Two of those statements look to be true. So the two statements that are true are B and C. Electron, the configuration is sigma 2s2, sigma 2s star 2, pi 2p y1, pi 2p x1 is the molecular orbital description of the ground state of diboron. And you could go back to the chart. So use the chart for B2, put 2 electrons in, and see you're putting each of the electrons in a pi orbital. In comparing the same 2 atoms bonded together, the blank the bond order, the blank the bond length, the blank the bond energy. Let's just go through. The greater the bond order, the shorter the bond length, that makes sense, and the greater the bond energy. That sounds about right. And let's just go through the other. So the greater the bond order, then the greater the bond length. That doesn't make any sense. So the greater the bond order means more bonding electrons, shorter bonds. So the greater the bond, the longer the bond. Nope, not true. That's just the same word as greater. So that's not true. Greater, greater, smaller does not make sense. Smaller, greater, greater does not make sense. So the smaller the bond order, then the longer the bond. So E is not true. So A is the correct answer. Which of the following is diamagnetic? So we know oxygen's para. You can put the electrons in the diagram if you're not sure, but that's why we did this whole MO diagram treatment. So MO is definitely paramagnetic. Unpaired electrons, if we have an odd count, should definitely be paramagnetic. And so by process of elimination, you can go with A. And of course, you can fill the electrons in and see it's just like F2. All the electrons spin paired for a diamagnetic molecule. Okay, well that completes. There's 1 or 2 problems that maybe are a bit specific to Dr. Loza's class. Maybe she has a few things that she tends to use in her lectures that I don't tend to use in mine. Maybe that's that one problem where I'm not understanding the coinciding of charge, what that even means. But it must be something specific to her class. When you see issues like that on some of these practice exams, I wouldn't worry about those issues moving forward. All these exams are written by committee, and the questions are vetted by several different types of people looking them over. So I wanted to go through this test just to go through a few of these problems. There are a lot of these problems with a lot of statements. Hopefully this video helps you better understand the answers to some of the problems in this test. Thank you for your attention.